In this video, we'll talk about Gauss' theorem, which can be used to relate volume integrals with surface integrals. Let us start with a quick recap of the one-dimensional version, which you hopefully already are familiar with. Make a plot with the derivative f of x on the y-axis and assume that we integrate from xs to xe. The solution to this integral is f of xe minus f of xs, which we have used many times already. One way to motivate this expression is the following. Define a point x and the second point x plus delta x. Now, let us look at the difference between f of x plus delta x and f of x. We can multiply and divide by delta x. And note that this expression is an approximation of the derivative of df dx. This means that df dx times delta x has the same value as the blue area in the graph, as df dx is the height and delta x is the base. If we assume that delta x is small, df dx can be approximated as a constant. Then, as the integral is the area under the graph, we can say that the blue area approximately is this integral. Let's introduce the next point, x plus 2 delta x. Use the same expression between x plus delta x to x plus 2 delta x. Then add these two equations together. Both f of x plus delta x terms cancel. Since both these are integrals of the same function, we can merge them into one integral of the combined interval. Repeat this idea for rectangles under the entire graph. This would end up with that f of xe minus f of xs is the integral of df dx from xs to xe. The final step is to let the number of rectangles go to infinity, which will make the area of the rectangles approach the same area as the area under the graph. Hence, we have motivated why the expression for the integral works. The idea with Gauss' theorem is that we are going to do the same with functions of several variables. We will do the demonstration in 3D. Here, our integration element delta v will have size delta x, delta y, and delta z. Assuming that the element starts as corners x, y, and z, we get the following for the corners. Let us start by looking at the x direction. Hence, add the normal vectors in this direction. We will also call the surface areas sx1 and sx2, which both equals delta y times delta z. We can then call sx the union between sx1 and sx2. Let us now consider the integral of the scalar function fn hat ds over sx, which means both sx1 and sx2. Then let us insert a position vector r into the integral. For this derivation, any position on the surface sx1 will work. To make it easy, pick the corner where the position is x, y, and z. N hat on the surface sx1 is negative x hat. The surface element is delta y delta z. Assume that the surface is small and that the function approximately is constant. Hence, drop the integral and multiply with the area. Continue with the second surface. Here we need to pick the corresponding corner on this surface. The normal vector is positive x hat. And the surface element is delta y delta z. Drop integral and multiply by the area again. Let the two terms swap order. We can see that x hat delta y delta z is a common factor. Then multiply and divide by delta x. Now we can identify this as the partial derivative with respect to x. Delta x delta y delta z is our volume delta v. If we assume that the f dx is approximately constant, we can say that this is the same as the volume integral over dv. We can repeat the steps in the y direction. Start by defining the surface elements and the normal vectors. This time the surface element is delta x delta z. We take the integral over both surfaces in the y direction. Again, the position vector should be any point on the surface. Pick the corner as last time. Normal vector is minus y hat. Surface element is delta x delta z. Drop the integral and multiply with the surface. The position vector for the second surface should be the corresponding corner on that surface. N hat is positive y hat. Surface element is delta x delta z again. Y hat delta x delta z is the common factor this time. Multiply and divide by delta y. This can be identified as the partial derivative with respect to y. And finally, assume that the f dy is approximately constant and rewrite as the volume integral. Finally, we have the z direction. The same pattern will repeat again. Hence, I will jump directly to the end expression, and we see that we get a partial derivative with respect to z now. The next step is to combine all 6 surfaces into one integral. Simply add them together. Now that we are integrating the same function every single time, just on different surfaces. Hence, we can combine it into one integral over the boundary of the cube. As all surfaces are included, it's a closed integral. These are instead all integrals over the same volume, and we can merge them to one integral. We can now identify this as the gradient of f. And we get the final result that integrating the gradient of f over the volume is the same as integrating f n hat over the boundary surface. For symmetry reasons, I will place n hat first, which will match future expressions in this video. This is one expression for the scalar function, but what if we have a vector function instead? Let us take the most common example where we integrate n hat dot b over the surface. In the x direction, this would give the following. N hat is minus x hat, hence we get minus bx, also inside the position. On the second surface, n hat is x hat, and we get plus bx at the position on this surface. The surface element is delta y delta z for both. Assume that bx is approximately constant, we can drop the integral. Place delta y delta z outside parentheses. Multiply and divide by delta x. And identify the partial derivative. Now, if the bx dx is approximately constant, this can be written as an integral over the volume. Continue with the y direction. It will basically be the same, but we integrate over sy and get the partial derivative with y. And the z direction will be similar as well. Then we can combine the expressions again when integrating over all surfaces. As we integrate the same function, we can merge the expressions into the integral over the full boundary. And the volume integrals can be added together. This can now be identified as the divergence of B. And we get the classical divergence theorem that the divergence of B integrated over the volume is the same as the flow of B integrated over the closed boundary of the volume. I want you to notice a pattern here. Compare how n hat and nabla appear in these equations. In the surface integral, we have n hat. In the volume integral, we have nabla. The operation between them, so the dot product or multiplication, stays the same for both sides. This pattern works for more operations as well. While I will skip the proof, we could do it for the cross product. We could also apply the dot product to a tensor of rank 2, which still follows the same pattern. What you should remember is that both the cross product and the tensor operation need to have n hat in front, as they are not commutative. That is why I placed n hat first in the other equations as well. These are 4 different versions of Gauss' theorem. A limitation right now is that we have only shown them for a very small box delta V. To extend this, let us consider what will happen if we place another box next to this one. Call the two volumes volume 1 and volume 2. The total volume is now the union between these. We can also write our equation we derived. Here the scalar version for both volumes. Then add them together. As the volume integrals are over the same function, we can write them as the integral over the combined volume instead. It's a little bit tricky for the surface integrals though, as we have these connecting sides in the middle. These are not part of the boundary of the combined volume. Hence, write it as the integral over the full boundary plus these. Now let us look at the normal vector, which for volume 1 is x hat. If you look at the normal surface for the second volume V2, the normal vector is minus x hat. These two integrals are over the same area and will hence evaluate to the same expression. And since we have a minus between them, they will cancel. The conclusion is that the original expression is true, even if we have the two boxes connected. We could of course add the box in another direction as well. For the connecting surface, we will again have opposite normal vectors, and the surface integrals will cancel. The final step is to look at the more complicated volume. Fill this volume with connected boxes, then let the number of boxes go to infinity, and we see that we can approximate this volume as well. Therefore, we can fill any region with boxes, and if they are small enough, the volume of the boxes will approximate the volume we want to integrate over. This means that Gauss' theorem works for general volumes as well. In the limit of infinitely many boxes, we can remove the approximation and write this as an inequality. If you want to apply it to 2D, simply replace the surface integral with a line integral over the closed curve, and replace the volume integral with an area integral. The derivation would work in the same way here. To illustrate Gauss' theorem, I will do one example. In the video about divergence, we had the following example, where we had divergence d inside a circle. No divergence outside. And we derived an expression for the radial velocity. This time I will show another solution using Gauss' theorem. Define the area we want to integrate over as the blue circle. The area has radius r and normal vectors pointing outwards. n hat dot v should be the velocity in the direction of n hat, which is the radial direction. Hence, this is vr. If we assume symmetry and that v only depends on r, then r is constant on our boundary. We can simply multiply by the length of the boundary, which is the circumference of a circle, 2 pi r. The integral will be valid for any radial position. For the area integral, we have two cases. Start with the case r is smaller than the divergence region. We know that the divergence is constant here. Insert d. A constant integrated over an area is just a constant multiplied by the area. We can divide by pi r. And we get our expression for VR. Let's go to our second case where r is bigger than the divergence area. As the divergence is 0 outside, we insert value d, but update the integral to only cover when r is small enough. This integral will then be d times pi r squared. Pi cancels and we can write the expression for VR. This gives the same solution as we had in the previous video. I'm going to end this video by mentioning Green's first two identities, which are closely related to Gauss' theorem. First, assume that f is some scalar times b. Then take the divergence of f. We can now apply the product rule for differentiation. Then we take the volume integral over both sides of this expression. As this part is the volume integral of a divergence, we can use Gauss' theorem and write it as a surface integral. As psi is a scalar, place it in front of the dot product. Another version is if we assume that b is the gradient of phi. Nabla.nabla is the Laplace operator. Here we have Green's first identity. These expressions are basically three-dimensional versions of integration by parts. Green's second identity is slightly more complicated. Let f be this expression. We do the same step and take the divergence of f. Expand using the product rule. These terms will cancel. Now we can take the volume integral of both sides. The left-hand side can be rewritten as the surface integral. Then place the scalars in front. This is Green's second identity. You will likely have to go a bit deeper into math before you need to use these, but as they are related to Gauss' theorem, I thought it would be good to mention them here. There is a third identity as well, which builds on the second, but it involves Green's functions, which we haven't covered yet. So I will leave it out of this video. This will therefore be the end of this video. In the next video, we'll talk about Stokes' theorem. Thank you.